Hello, welcome back to our channel, and we continue our discussion of linear IC voltage regulators. So if you can recall, in our previous module, we covered the basic principles of the design of the voltage regulator, and in particular, we talk about design analysis and simulation of the standard or typical voltage regulator that you see currently on your screen. And we got the equations, and we covered the fundamentals about how this circuit works. We also emphasized about why it is called a standard regulator, and there we use this Darlington pair as a series pass transistor or power transistor that delivers the current to the load. And we then said, okay, this PNP transistor acts as a drive to this transistor, and this NPN transistor acts as a drive to this transistor. And the base voltage, which is a kind of control voltage, comes from the output of this error amplifier, which has two inputs, negative and positive is connected to the fixed reference voltage, and negative is connected to the voltage that is obtained by the voltage division through these registers R1 and R2. And we said that, okay, this is our unregulated power supply or voltage supply source, which is about 15 volt, for example, or let's say V in, and this was our V out, and we said that V in minus V out, which becomes the overdrive VD, overdrive voltage, which is a differential between these two. And we said that in this is a standard regulator that over voltage should be about 3 volt or more. And we said that, okay, we wanted 5 volt in the output. So this is sufficiently greater than the output required. So 5 plus 3, we want 8 volt minimum, but we have this 15 volts, so it's essential. And then we said that this kind of regulator is used to supply a maximum load current is about 1 ampere. And then we got the operating point analysis dot op, then we got the DC analysis. For example, operating point analysis showed us the different voltages and the currents of the circuits, devices, and all the components. Then dot DC analysis showed us if we sweep the voltage, input side voltage, like we reflect the fluctuations, we mimic the fluctuations in the input power, and then we obtained the constant voltage despite that fluctuation. And then we had this step parameter. For example, instead of fixed value, we in the parentheses we put up the x parameter x, and then we stepped that parameter x from the minimum value to maximum value with the steps of 10. And then we again said that for the values of x, your output voltage was about constant, or maybe a variation, there was a little variation. So we got this load regulation and line regulation. Okay, so our circuit was in that case. We also said that this with a dual power supply that is providing the positive and the negative supply rails to the operational amplifier. And we also covered why we chose these transistor from the manufacturers. We right click through the spice library, and we got the specification about IC max and then VCE max of all the transistors. So with that said, now we are going to talk about another circuit, which is a modification of this circuit. So we are talking about LDO. So let me take you to this circuit now, which is, and let me clear all the drawings. So this is a fresh circuit. You see Instead of a Darlington pair, we are using single PNP transistor. This is your PNP transistor because of the direction of the arrow. This is an emitter, this is a collector, this is a base, and the current is flowing from emitter to the collector. So you have an input voltage, which is V1. I am showing it is a pulse that was done for another analysis, but we don't need a pulse right now. We are talking about the DC analysis. So what I'll do, I'll right click this voltage supply and I click none, and then I am able to select the DC volt. So for example, I want to design a power supply, a regulated power supply for a fixed value of 5 volt, just like before. So I will choose the input value. Remember, this is a low dropout voltage regulator. So there is not a harsh requirement or necessity to have input voltage 2 to 3 volts larger than the output required. It is about 100 millivolt in a best case, but still we will say, okay, 1 volt V in is 1 volt greater than the required output. So I will choose it here 6 volt, and that's it. And the output required is 5 volt. So this kind of arrangement I am calling a design of LDO, which is low drop out voltage regulator. And we are talking about designing it. Now, with this input unregulated, this is unregulated voltage source. We have this input current I coming, which is nothing but your IE. Okay, this is your IE, and this is your IC, and this is your IB, that is the base current. This IC is then split up into two parts. So the current I, let's say IR1, and this is also the current IR2, that is the current through these one. And then the another part is your final part is the load. Okay, so you can see now the IC is equal to I R1 comma R2 plus IL. So I1 R2 is the current flowing through these resistors, which is while designing we make sure that the minimum current flows through them, because they are just there to provide the bias to the error amplifier and sense the feedback voltage. They act as a feedback control circuit. We'll explain that in a moment. So this is, and finally, approximately, if we neglect the current through them, IC is approximately equal to IL, because we say that IR1 or R2 is very small. So choosing the high values of the resistors can make sure that the current flowing through them will be pretty small. So I, input current I, is your current IE of the power transistor. This transistor is acting as a series pass transistor. Series pass transistor, or also called as power transistor, because this is the it is called a series pass transistor because it forms the series. It's in series between input and the output. That's it. Then we say that V in minus V out is equal to VD, which is VD is your overdrive voltage. Overdrive voltage, which is a differential voltage or difference between V in and V out. So with value of 6 volt at the input and required value of 5 volt at the output, we say that VD will be 6 minus 5 will be approximately 1 volt. So as long as you will maintain this 1 volt, your circuit will ensure the regulation. If your overdrive is less than that, we are talking theoretically. If it falls less than 1 volt or falls to a very low value, circuit comes out of the regulation. That's what we would like to see. Maybe we can reduce the value of input below 5 volt, and obviously we'll see that circuit is no longer uh, maintaining the regulation. And the product of IL times the VD is your power dissipation in the circuit. Okay, that is the output power. This is the output power. So let's say you have a requirement of 50 milliampere, or let's say 100 milliampere. Let me correct it. Let's say you have a requirement of 100 milliampere. We'll see that how much it is. So power dissipation, output power will be 100 milliampere multiplied by 1 volt. So it is 100 milliwatt power consumption of that circuit will be. So it all depends on that, right? So you have this now. This is your collector of the NPN transistor. This is your emitter, and this is your base. And there is a current that is IC. Actually, this is the collector current IC. So essentially, you see the direction of the currents here, IC. Then here is your base current IB, and that is your current IE. So what happens, this node voltage, which is at the middle point, where your output voltage right here or right here is the same node, is sensed by these resistors forming a voltage division. And here at node A, that voltage is sensed, which is applied to an error amplifier, the negative input of the error amplifier here, and the positive input is connected to the reference voltage, fixed reference voltage, which is set at half the required voltage of 5 volt. Okay, and in the previous case we had seen that the output voltage V out is given as V reference in bracket 1 plus R1 over R2. That was the case. So if you want it to be 5 volt, this is of 2.5 volt. So you need to choose the value of resistors R1 and R2 to give you that one. So if R1 and R2 of equal value, then this term will become 1, and 1 plus 1 equals to 2, and 2.5 multiplied by 2 becomes 5 volt. So we have chosen, let's say, 50K each, these values for here. Power supplies, dual power supplies are the V plus and V minus. They are plus minus 10 volt. Now look, output of this error amplifier is becoming an input to this transistor Q4. You see this node and this node, this label of the nets, this net and this net are same. So they are the same nets. Similarly, this net has a label of A, and this net has a label of A. So they are the same net. Net is just a wire. Okay, so we are done. Now you want like IL is about 100 milliampere. So what should be the value of RL? So 5 volt is your output divided by 100 milliampere is the current requirement. So what should be the value of your resistance RL? So RL is going to be how much? Let me check. Use it right here. It comes out to be 0.05 kilo ohm, right? So 0.05 kilo ohm is like 0.05123 ohm. So it's about 50 ohm. So that's much. So I think the current is still high. What about the 10 milliampere? So 5 divided by 10 milliamperes. So it will be like um, 500 ohm, 500 ohms. So why not change that and see how much current we see that, okay? So let's change the value to 500 ohms. So that's it. So now what we are going to do, we will just run the operating point analysis. Before that, I forgot to tell you, but I will not repeat because we have covered that in the previous. These are all the parameters of the operational amplifier. Like I have chosen the gain of the amplifier, open loop gain to be 1 mega, its gain bandwidth product to be 10 mega, offset voltage is 0. So it is a universal amplifier I have chosen. So I want to run this analysis, that is dot operating point analysis. So I have from the previous case, I have disabled this by putting this epsilon sign, but not epsilon sign, but just a comma. So what I'll do here, I will just right click here and enable this command so that, yeah, right click, and you see now with this, I will just delete that sign, click OK. This command is now back in action. So what I'll do, I will just go to simulate and I will click run. Now it is asking me the DC operating point again. So let me draw it. OP, missing nodes. So there is some problem here. Okay. You see here, I have chosen, I have put up this command 2 times actually, right here and right here. So it's 2 times. So I don't need that. So just cut it and maybe save and then run. Oh, it's still asking me that. OP. Okay, best way is to just delete them all. Delete it. This also delete it. And this also you delete it. And then just save and simulation, edit one, DC operating point. Let me take it here, OP, and then click OK. Put it here somewhere. We'll see how it goes. Oh, voila, done. So we are done with these results, and uh, we have successfully completed our operating point analysis. So look at here, your input voltage is 6 volt V in, your output voltage is 5 volt, what we want. Voltage at the node A is 2.5 volts. So node A is here, right here, you see, because it will be half of the output voltage because of the voltage division. Then voltage at node, no, not 2. So what is that node? We don't know because we haven't defined this one. So most probably it is like this V reference, not the V reference. Yeah, it's probably this node. Then these are the power supplies of the operational amplifier or error amplifier. Output of the error amplifier is 0.5 volt, which is applied to the base of the transistor. Then voltage at the node 001 is 5.3 volt. These are the currents of the transistor Q2. Where is transistor Q2? This is your series pass transistor. So let us investigate the current through them. So you see the collector current is about 10 milliampere. What is this is what we have required. You see, this is the collector current that will flow here, which is the load current. And the base current of the transistor is about 27 microampere, and the emitter current is same as approximately 10 milliampere. Now transistor Q4, it has its value about 27 microampere is the current through the collector, and then base current is 69 nanoampere, which is reasonable. and the emitter current is again approximately 27 micro. So you see the collector current of transistor Q4, which is here, is just 27 microampere, which is becoming a base current of your transistor Q2, right? Because IC and IB are same right here. But the collector current of Q2, which is a PAR transistor, has a collector current is about 10 milliampere, right? 10 milliampere right here. So which is our load current, and that is what we designed it for. So it's perfect. Now the current flowing through IR1 and IR2 is 50 microampere. That's what we designed it. We initially said we don't want, we want the current through IR1 and IR2, R1 and R2 to be as small as possible so that whole current IC gets delivered to the load RL. Now that's what happened here. So total current supplied by the source is about 10 milliampere, approximately 10.7 milliampere. Your current from the reference is nanoampere. I of V3. What is the V3 here? Yeah, there's a supply currents of the operational amplifier voltage sources. And now this is IX, U1, U2. These are basically your sub-circuit currents, that is, which is inside the operational amplifier. So you see, this is pretty good. And we got this constant voltage of 5 volt here. Now, the second part is to simulate the line regulation and the load regulation. So load regulation is the percentage change in the output due to changes in the load. So it's in a modern devices or ICs, it should be about 2% or 3%. Similarly, line regulation is a percentage change in the output due to change in the input. So it is again in modern sophisticated ICs, it's about 1% to 2%. So what we are going to do, we are going to vary the load and see how that changes. So let me in the parenthesis, we are just repeating what we did in our previous module. So because you know the numbers now, how much is the load, current requirement, output voltage, input voltage, everything. So why not just let me clear the drawing first. Clear all the drawing because you know equations, you know the numbers and everything. So why not just then come back here and you see to the load, I will just use the parenthesis and I will just click here. Okay, that's it. And I will now enable this command, right click and just remove this here. So it is dot step. So I'm stepping this parameter X to the values. It had a value of 500, right? So let me have a maximum current. So for example, it goes to 500, then it comes to 100 at the step of 100, for example, or 10 just. So it will start from 500, then it will come down to 100 ohms. So it means the load current will be maximum. So the circuit has to deliver more and more current to the load, and we'll see if the output voltage can maintain the regulation to that. So done. Click run simulation and voila. So this is our previous circuit of the standard. Just close it. Yeah, okay, save the changes and tile the windows. Now you see what I want to plot is output as a function of load resistance values. So pretty good. It's like from 100 ohm to 500 ohm. I have a 5 volt. Very good. What about I right click on the schematic? Let's say I go to 10 ohm, more current, and click again. Now you have a problem. So your output is perfectly fine if you have a volt resistance of 40 ohm lowest. It means 5 divided by 40 ohm is the maximum load current that your circuit can supply to the load under these conditions. 5 divided by 40. So how much is that? So for a current, maximum current that your circuit can supply to the load is 5 volt divided by 40 ohm, which is 0.125 ampere. So is 125 milliampere. That's it. If you drop below that, your regulation is gone. You don't have a regulation there. It still can do that, but you have this change. Your output is varying from the constant value. Is that so? Looks like that. So just right click and zoom to fit. Okay, and what about you have a higher values of the load? For example, right click, you start from, let's say, 5,000 and you go to about, let's say, yeah, 10. Maybe do it again. Yeah, you don't have any problem with the minimum value of load. So that's how your dropout uh, voltage works, right? So that's it. That was about your load current. Come back to your screen, and here it's your output. Now let me clear all drawings. So that's it. You are done with these load. What about now we check the line regulation? So what we'll do, we'll right click this command. We'll disable this command. We don't want that, and we want to sweep the DC voltage. So we'll do that. Then operating point also we don't want, because we are going to do the DC sweep. And then right click the voltage source. Okay, it is like that, but then simulate, edit simulation command. Here we click DC sweep. Name of the voltage source is V1. This is what we want to do. Linear. Start value is like, say, 6, and we want to stop value is like, let's say, 2 volt, and increment is 0.5 volt. So it will start from 6 volt, which is currently working fine. It is maintaining the regulation. Not the maintaining the regulation, we'll say it is giving us the constant 5 volt. And if the input drops from 6 to 2 at the step of 0.5 volt, we'll see if the output voltage remains constant or not. So we'll click run. Okay. You have to choose your load. So now 40 is the lowest value of a load. Let's say you keep it 100 ohm, and we'll see that now. So your input is swept from 6 volt to 2 volt. What about the output? Voila. So you see your output is about 5 volt for the value of, but input is up to this point. So right here, your input is 5.5 volt. From 6 volt, it fell down to 5.5 volt. So the overdrive voltage, which is the differential between V in and V out. So V in minus V out is 5.5 minus 5. So it's just 50 millivolt. So that is the lowest overdrive voltage the regulator want across the input and output, across it. If your input falls below 5.5, like 5.48 and so on, your output is leaving the regulation zone and it is dropping dropping down. So that's it. So you want to make sure you have reasonable headroom between input and the output, and after that your output is zero. But you don't even think about this. You are concerned about only this section. Your output is constant up to input voltage of how much is like 5.5 volt. That's it. So very good. We have successfully covered the design, analysis, and simulation part of low dropout voltage regulator, a linear regulator, low dropout voltage regulator. And this is a type of linear regulator. And wonderfully, we have seen all the details through the circuit simulation, how this voltage maintains a constant regulated output of 5 volt despite the changes in the load and the changes in the input. So if you like this video, click like, comment on the video, do share with others for a wider reach, and stay tuned for more technically rich and informative contents on analog and mixed signal designs and the sensing and the sensor circuits on our channel. Till then, wish you happy learning.